All right, to explain the shape of the molecular orbitals of benzene and aromatic compounds, so we're not going to get into the math, the heavy math stuff behind it, okay? But we're going to use different tool. This tool is called Frost circles or Frost diagram, developed by Arthur Frost from Northwestern University back in the day, right? So the Frost circle goes like this. So first off, you draw a circle, okay, and take your pen or pencil, and we're gonna start right here. You're gonna draw the shape of the compounds that you're about to determine aromaticity. Okay. For example, in this case, we do benzene. So you're going to draw a hexagon. Start with the edge, just one edge down here, and you go hexagon. Look like this. Try to make it as symmetrical as possible. Okay. Once you have this, each edge of this hexagon is each molecular orbitals. Okay, so we have type 1, 2, 3, 4, 5, and 6. Frost circle accurately predicts the energy gap between molecular orbitals from the calculation, from a lot of calculus behind it. Really, really easy and simple. Okay, let's try with this cyclobutadiene. Now I start with a circle, and you're going to start with at the bottom. Take one edge of this square. You're going to draw a square. Okay, so go like that. Here we go. And all these edges, those are molecular orbitals of a cyclobutadiene. Yeah, super simple. If you do a three-membered ring, 4, 5, 6, 7, 8, you're gonna get all this. These are Frost circles or Frost diagrams. All right. All right. Here's just for our communication. If you draw an imaginary line, go through, like cut all the circle in half, the molecular orbitals that falls onto these lines are called non-bonding molecular orbitals. Anything below it we call bonding molecular orbitals. Anything above it we call anti-bonding molecular orbitals. Okay, but again, I still haven't answered why 4n plus 2. Okay, if you remember 4n plus 2, so we go like a 6, 10, what else? Not 12, 14, 18, 22, and go so on. Okay, let's do something that doesn't go 4n plus 2 first. The following are not aromatic. We call anti-aromatic. Actually, all right, let's do 4 pi electron system and pi electron system. These are anti-aromatic. But how come though? Let's take a look. 4 pi electrons. Now we're gonna have add all 4 pi electrons in this diagram. Okay, so 4. I'm gonna go start from the bottom, the lowest energy level, 1 and 2. Go up to the next one, 3 and 4. Now you can see that this guy have an open shell electron configuration. Has nothing to do with these 2 electrons are on non-bonding or anti-bonding MOs. No, we're not talking about those. Okay, but these 2 clearly, I mean, like this diagram clearly show that cyclobutadiene contain an open shell electron configuration, and that is anti-aromatic, not stable. Try 8 pi electrons. Okay, so we have 8 total to fill. So start with the bottom one, 1 and 2. 3, 4, next level, 5 and 6, same level. Now 6, 4, go to the next level, 7 and 8. Now that's an open shell. Yeah, not stable. If the number of pi electrons follow 4n plus 2, let's see what happens. So I start with 6 pi electrons, like in a benzene ring. Okay, so 6 electrons will go 1 and 2. Go to the next energy level, 3 and 4, 5 and 6. That's a closed shell. Love it. Very stable. 10 pi electrons also follow 4n plus 2. Start from the bottom. 1, 2, 3, and 4, 5, and 6. Go to the next one. 7, 8, 9, 10. Closed shell. Love it. So that's an aromatic compound. This is a Haeckel's rule, and use a Frost diagram to explain it. Now we have seen that the cyclobutadiene is not aromatic. Actually, it's an anti-aromatic, so not stable. Okay, so to avoid that, cyclobutadiene does this. Instead of have the resonance stabilized resonance structures, all this carbon-carbon bond are 1.5 bond, like in the resonance structure of benzene, but it doesn't do that. It leaves a pair. 2 of the 4 carbon-carbon bond single bond, and the other 2 double bond. To doing this, this p orbitals and these 2 p orbitals are not conjugated. Okay, they are not conjugated. When it's not conjugated, it can avoid being anti-aromatic. All right, so these two structures are in equilibrium, not in the, like a resonance structure of benzene. All p orbitals allow electron to delocalize, but this one is not. Okay, so basically this guy end up have two single bond and two double bond. These two double bonds acts isolatedly. They are isolated, two isolated double bonds. The other case that we talk about, cyclooctatetraene, this one, so if all these four pi bonds are in linear, they're going to be anti-aromatic, not stable, right? To avoid that, cyclooctatetraene, they flipped just the end, this two double bond up a little, make all the p orbitals not overlap to avoid being anti-aromatic. That's how I do it. All right. All right, let's do this. So review one more time. So there are three criteria, okay, of being aromatic. We have being planar, cyclic conjugated pi system, and the number of pi electron must follow 4n plus 2. Let's do this problem together on your own. Okay, I mean, have you do on your own first and check with me on the next video. Okay.